Okay, so now in this video, let's apply some of these linearization techniques that we've been developing back to the original motivating example for the pendulum. And so in particular, we want to identify whether the critical points, the equilibrium for the pendulum, whether those are stable or unstable. And so we've already identified what the equilibrium are. Namely, we said that if we've got conditions theta v, first of all, if the pendulum isn't going to move, if it's going to remain constant, then v, the velocity, needs to be 0. And secondly, we noted that the only times that the pendulum is going to be in equilibrium if it's located vertically perfectly at the top or hanging perfectly vertically down. And so here, these would be situation where we have k times pi for k an odd number, and this would be the scenario where we have k times pi for k an even integer. And we've already thought about this intuitively as far as are these going to be stable or unstable. And we kind of suspected that if it's hanging up in this precarious position over here, if you initially set it up just slightly off from those conditions, we would expect that as time goes on, it's not going to move back to that position, whereas that is the case over here. So let's kind of verify all of our intuition with the math that we developed over here. And so just to make things a little bit simpler, since we already have enough letters going around, and so if we replace theta with x, and if we replace v with y, so that we have our usual x and y's, then maybe this will be a little more familiar. So then the top equation becomes dx dt is equal to y, and the bottom equation becomes dy dt is minus the sine of x minus 0.2 y. Okay, so now it's a little bit clear what I'm considering my x and what I consider my y. And so if I want to identify or classify each of these equilibrium as stable or unstable, then what we can do is find the Jacobian, which is the matrix of partial derivatives. And so if we take the partial of f, okay, where now f is the top function over there, its partial with respect to x is 0, and its partial with respect to y is 1. And then we would take a look at g, which is the equation for dy dt, and taking the partial derivative of that with respect to x would give me minus the cosine of x, and taking the partial derivative of that with respect to y would give me minus 0.2. Okay, so when we want to determine the stability for these equilibrium for nonlinear systems, we find this Jacobian matrix, which is equivalent to doing that linearization process. And then for each of the equilibrium, we need to plug in our values for x and y and get constants in the matrix. So in this case, we have kind of two sets of equilibrium. So we'll say like case 1 is going to be that this integer k is even. And so that means we're dealing with things that look like k being an even number, pi 0. And so that Jacobian, therefore, would be 0 and then 1, and the minus 0.2, that's going to be the same for all of them. But if I were to plug this into the cosine function, if k is an even number, then the cosine of k times pi is going to be positive 1. And then we multiply that by the negative in front, and that would be our corresponding matrix of coefficients for that linearized system. And when you want to calculate the eigenvalues for this matrix, let me just say they're going to be complex. So these are going to be things that look like the real part is minus 0.1 plus or minus some beta I. Okay, it doesn't work out particularly well. But when we want to identify whether this is stable or not, if we have complex roots, since this is a negative real part, then this is going to be a stable spiral. So that's what we imagined would happen, that those are equilibrium, and they're stable equilibrium. The second case is, what about when k is odd? And so when that happens, our matrix is going to be 0, 1, minus 0.2. And now when I plug in something odd times pi into the cosine function, if k is odd, we're going to get negative 1. So then we get negative 1 times negative 1, and we get a positive value over here. And when you find these eigenvalues, they are approximately 0.9 and minus 1.1. So they're real. One of them is positive, one of them is negative. So this actually winds up being a saddle, and we would say that that is unstable. So really, to summarize that process, is we want to find the Jacobian, this matrix of partial derivatives. Then we evaluate the Jacobian at each of the equilibrium points. And then we look at the eigenvalues of those corresponding matrices. So we do the same analysis at that point as we did with linear systems. So there's a big space over here. Here's a surprise. Here is the phase plane plot for the pendulum that we've seen before. And what we can see is that when k is even, kind of lost sight over here, these are these spiral stable equilibrium. And when we multiply it by an odd integer, then we're at multiples like pi and 3 pi and so on. These are unstable. So these are actually saddle points. So there are some eigenvectors that go in here, and this one would be going in, and whoops, this one would be going out. So these are these little saddles. And so when we're looking at this trajectory in the phase plane, this would be like, okay, here's the equilibrium if we set it up so it was perfectly standing straight up, right? Its velocity is 0 and its position is at pi. But if we are just off from those initial conditions a little bit, so in other words, I have it perfectly lined up at theta, but it's moving a little bit, then as time goes on, it's not going to settle back down to this point. It's going to continue to move to the right, and then it's going to settle back down, back at its bottom, which would correspond to an initial, or would correspond to a value of theta which is equal to 2 pi, meaning it went one full rotation around and then stopped back at its downward hanging point.